Well, hi everybody. Thanks for checking out my video here. Just wanted to kind of cover something that I think I can do pretty easily in this little short video that will save us some time in class so we can spend more time talking about homework problems and kind of moving on into chapter 12 a little bit further. So thank you for tuning in. Hopefully this will all make pretty good sense. I'm just going to quickly overview position, velocity, and acceleration vectors, and then just do one example. And that's really all I feel that we really need to do with this section. So we started talking about vector-valued functions. And of course, the R of t is the notation for this vector-valued function. And it has components that are themselves functions of, well, I use t for that for time, right? So we have x, y, and z coordinates of our position vector that are changing with time. And that is what we talked about before, and that is the position vector. Okay? We talked about taking derivatives of the position vectors, among other things. And when you take the derivative of the position vector, we're going to get what we call the velocity vector, right? The derivative of the position, the rate of change of the position is the velocity. And that is r prime of t, and you simply calculate the slot-wise derivatives of the position vector in order to get the components of the velocity vector. So nothing surprising about that. And then, in fact, we can do it again, right? We can take the velocity vector and take another derivative and get our acceleration vector. That's r double prime of t, and here you see that it is just two derivatives of each slot of our original position vector to give us the acceleration vector. So just to have a little diagram sort of summarizing these relationships, I can draw a little picture. I don't even know if you need this picture to understand this, but it just, for me, sometimes I like to have a visual. So here's r of t, which, as I said, this is the position. Okay, and then if we come across here, by taking the derivative with respect to t, I'll just denote that with this little Leibniz ddt expression, well, then we get the velocity vector, r of t, r prime of t. That's the velocity vector right there. And then if we do this again, we're going to get to the second derivative of the position vector, and that is the acceleration vector. Okay, so here it is right here. I might also mention that if we take the velocity vector and we actually take the norm of it, so this would be the norm of r prime of t, that represents, as you probably are aware, that represents the speed of the vector. So remember that this position vector is tracing over time the path of some particle, right? So at any given time, the particle is somewhere in our three-dimensional world, and so we can wonder, well, how fast is that particle moving, what's its velocity, acceleration, and so on, and these are all of the relationships that you would need for that. Of course, the magnitude of the velocity vector is going to be in terms of a radical, right? So we would take the square root of the sums of the squares of the individual slots in order to get that. So this would be the actual formula, and this again is not a vector, right? The speed is not a vector. This is a scalar expression. It might depend on time t, okay? So it may not be a constant value, a numerical value, but it certainly is a scalar value, which means it does not have components. It might have t's in it, but it does not have components, okay? Now, most often in the real-world problems that you encounter involving these variables, or involving these functions, I should say, it's the position vector that you want to find, and you may not have it at the beginning, right? You may not know the position of your particle at any given time, but you would like to figure it out. And a lot of times in real-world problems, we do know the acceleration in advance. So although I've kind of given you the notes sort of from top down here, position to velocity to acceleration, it's often the acceleration that we know up front, and we use that to go backwards and get the position. Okay? Let's talk about a baseball. that's flying through the air. We may not know at any given time where that ball is at, but we do know that it is subject to a gravitational force which is going to give us the acceleration vector. Okay, so let's talk about that. Let me make up an example here. So a baseball player throws a ball 90 feet. So he's going to throw the ball 90 feet to first base. Okay? So he's going to throw the ball. It is released, the ball that is released 5 feet above the ground. That's where the arm of the baseball player is. So 5 feet above the ground is where that ball is going to get let go from, with initial velocity. So this is going to be this is actually, it says initial velocity. It's really the speed because it's just a number. So at time 0, at the moment he throws the ball, it's going to be traveling 50 miles an hour at an angle of 15 degrees above the horizontal. So, and here's the question: at what height does the player at first base, catch the ball? Okay. This is going to be the question. Okay. Let me come over here and draw you a little picture so you can visualize what's going on. This is a sort of a classic physics problem. Just involves distance, velocity, and acceleration. Position, velocity, and acceleration, right? So actually, let me draw the picture right here. It might make more sense to do that. Here's the ground. And let's say that this is the baseball player right here. And if this is, say, 5 feet above the ground, okay, he's going to launch the ball at 15 degrees right here. And somewhere over here, 90 feet away, right, this is going to be the height that we're looking for. So we're trying to figure out how high above the ground is the ball when it gets caught. 90 feet away. So this trajectory of this ball is what we are very interested in here. Okay? What sort of things do we know ahead of time here? Well, we do know that the position of the ball at time 0 is right here. Okay? Let's just put our y-axis, this was the ground is the x-axis, let's put our y-axis right at that initial point. If we do that, then this point, we can actually label that position with an x-coordinate of 0 and a y-coordinate of 5. So this is going to be a problem that only has 2 components, the x-coordinate and the y-coordinate. Okay, and then the other thing that we know is that, I should mention that the 50 miles an hour should be converted into units of feet, because that is what all the other units are given in, is in feet, 90 feet, 5 feet, and so on. And if we're going to convert it into feet, then converting from miles to feet is going to give you several thousands of feet per hour. So let's convert it into feet per second, and it comes out to 73 1/3 feet per second. I'll just abbreviate that like this. It's just a little easier to use feet per second, okay, so that we can make use of all of these values here. So if I want to look at the initial velocity, that would be r prime of 0. Well, it's 73.3 feet per second at an angle of 15 degrees above the horizontal. So what that means is that if this is 73 1/3, I have to multiply that, so that's the speed here, right, in this direction, but I have to figure out what is its x and y coordinates, right? What are the x and y components of that velocity? So that's going to require me to take the cosine of 15 here, and in the y coordinate, that would be the sine of 15 degrees. Make sure that your calculator is in the correct units when you're doing this. We will use a calculator for this, but that's going to be important. This turns out to be approximately 70.83, comma 18.98. So the ball has both a horizontal and a vertical component to it as it's being released and thrown through the air. And these are what those feet per second values are going to be. So we know the initial position and the initial velocity, but we really are trying to find out when the ball reaches 90 feet, which we don't know yet when that is, but we would like to know what is its y coordinate, right? So we would like to know that, but we're going to have to do a little work to figure out the time when that happens. Now, as I was saying earlier, a lot of times we know the acceleration up front, and we can use that to sort of work backwards. The acceleration in this case, that's the r double prime of t. Because this ball is being subjected only to the influence of gravity, right, which pulls the ball straight down to the ground, that's the only force acting on it. There's no horizontal forces on that ball, right? Once that ball is sort of in the air, it's just undergoing free fall. It's just falling freely through the air. So there's no x or y force to the ball at that time. And there is a y coordinate to the ball, and it's a negative one, a y coordinate to the acceleration of the ball. It's negative, and it turns out that near the Earth's surface, it's approximately negative 32 feet per second squared. So this would be the components of the acceleration of this ball, and that is actually for any time t, right? The Earth's gravity is always acting on the object with this horizontal and vertical component to it. So that's going to make it somewhat easy to figure out. What we have to do now is we have to integrate this twice to get our position function. So when I do one integration, I'll get back to my velocity. Of course, the integral of 0 is 0 plus a constant. I'll call it c1. And the integral of negative 32 is negative 32t plus c2. All right? And now here is where you can evaluate this at time 0 to figure out what c1 and c2 are. If you plug in 0 for the time, of course you're going to get c1 and c2, and we already know what r prime of 0 is, right? So c1 has to be 70.83 and c2 has to be 18.98. So we know that r prime of t is going to be, the first component is 70.83, and the second component is negative 32t plus 18.98. So that's pretty easy. So we got our velocity at this point. Okay, I'm going to go ahead and erase this question. You can always rewind or put this on pause at some point if it would help you. But we're just trying to find r of t, and then we'll go from there. So to get r of t, I'm going to do another integral. I'm going to integrate the velocity function that I just came up with. So that's going to give me 70.83t plus what I'll call c3, of another constant of integration. And then the second component, negative 16t squared plus 18.98t plus c4. Like that. Okay, and again, I know what r of 0 is, so if I evaluate r of 0 into this expression right here, I just get, c3 and c4. Everything else cancels with when you plug 0 in for t. Okay, so c3 has to be 0 and c4 has to be 5, right? Because this was given in this manner. So I finally have r of t. It is first component 70.83t plus 0. And the second component, negative 16t squared plus 18.98t plus 5. Just like that. This tells me at any time t, this is going to tell me what the position of the ball is, right? Now, we are interested in figuring out the vertical component, the height above the ground for the ball, when the ball gets 90 feet away from where it started. And that was 90 horizontal feet, right? So what we are going to do to figure this problem out is we are going to set the x component, the horizontal component of the position vector, equal to 90, because that's going to allow me then to solve for t. T is going to be 90 divided by 70.83, which is approximately 1.27 seconds. So the ball gets to first base after 1.27 seconds. Okay? Now, on the other hand, what we really are trying to find is this value right here. How high above the ground is the ball at that particular time when it reaches first base? So what I have to do is plug in 1.27 seconds into my position function. We already know that the horizontal displacement will be 90 feet. And when you plug 1.27 in for t here with a calculator, of course, you're going to come up with 3.27 feet. And that is the answer to the problem. Okay? So there you have it. All right? So the idea is we assume that the acceleration due to gravity is given by this vector right here. It's just a constant vector with a downward vertical component, right, and no horizontal component. We can integrate it twice, which is what we did, and use our initial values, our initial conditions, to actually plug numbers in to find what those constants that show up, the C1, the C2, the C3, and the C4. We can figure those out, right, by plugging in the t equal to 0 information. Once we've got this position vector right here, this is the whole goal, we can now answer just about any questions that we might get asked, including the one that we just addressed right here. So, anyway, I hope that makes sense. Just a quick little rundown on position, velocity, and acceleration for you. Of course, I'm going to be happy to talk about this some more. We can try some practice problems from the homework and whatnot, and you know, have a chance to sort of clarify this further and just practice it a bit. So anyway, thank you guys very much for watching. Hope that it makes sense, and I'll see you all soon. Thank you.